right? So we're diving into this paper today, Runtime Verification for Trustworthy Computing. I know you're no stranger to the complexities of machine learning and all that, but as we get deeper into like autonomous systems and robotics and stuff, security, it becomes a really big deal.
Right. Yeah.
And this paper is really all about how to make these systems, especially as they get more and more sensitive and complex, how to make them truly trustworthy.
Yeah, and what I find really interesting about this paper is it doesn't kind of shy away from like the hard realities of cybersecurity, you know? They bring up things like the Heartbleed bug in OpenSSL and the Spectre attacks, these vulnerabilities that that exploited speculative execution.
Yeah.
It's a good reminder that even these well-established technologies, they can still have weaknesses.
Right, right. And it almost seems like they're saying, traditional security, like, it might not be enough anymore.
Yeah.
Especially with these increasingly complex systems, like you mentioned, robots and autonomous systems. It's not just about like protecting data anymore.
Yeah.
It's almost like making sure these systems behave the way they're supposed to.
Exactly, yeah. The authors, they really advocate for a risk-based approach to security. So basically, the more sensitive the application is, the stronger the protection needs to be.
Yeah.
Makes sense.
Yeah, it does.
And, as robots and autonomous systems, they're handling more and more critical tasks these days, right? We've got self-driving cars, infrastructure management, all sorts of things.
Right.
And, if there's a security breach in one of these systems, the consequences could be pretty serious.
For sure, for sure. So how do they propose, like, how do we get to this higher level of security? They talk about these things called trusted execution environments, or Ts.
Right.
I'm guessing it's not just like building a digital wall around our code.
Yeah, no, it's definitely more nuanced. That Ts are basically like these secure enclaves within a system,
Yeah.
They isolate sensitive code and data from the main operating system.
Yeah.
So you could kind of think of it like a secure, isolated data pipeline within a larger, messier data lake, if you will.
Okay. Yeah, I get it.
Yeah, so you're basically ensuring the integrity of these critical processes, even if the surrounding environment gets compromised.
Makes sense.
And they mention a couple of existing technologies, Intel, SGX, and ARM Trust Zone. These are both hardware-based Ts that are gaining some traction in the industry.
Right.
But they also acknowledge that even these technologies have their own vulnerabilities. Nothing's perfect.
Right, and that's where the core contribution of the paper comes in, right?
Right.
With this RVT thing.
Exactly.
It's like combining this runtime verification, RV, with a hardware security module, or HSM.
Right.
So it's kind of like adding another layer of protection on top of the T, right? Like, we're not just blindly trusting the T, we're actually verifying what it's doing in real time.
Yeah, that's a great way to put it. So our RVT, it monitors the T's operations, and it extends this monitoring to a zone called the rich execution environment, or RE.
Okay.
It's kind of like establishing an intermediate level of trust, between the T and the rest of the system.
I see. So it's like a buffer zone almost.
Yeah, exactly. Like, think of it as creating a buffer zone around that secure data pipeline we talked about.
Right, yeah.
Making sure that anything that interacts with it is also behaving as expected.
I got it. So why is this intermediate zone, this REE, so important? Why not just keep everything inside the P, completely locked down?
Well, in real world applications, it's really hard to completely isolate trusted code.
Right.
Certain operations, they just inevitably need access to resources or data that are outside the T.
I see.
So the REE provides a controlled environment for these interactions. It's like extending that security perimeter without compromising the core integrity of the T itself.
Okay. So we have these different levels of trust: the T, the REE, and then the rest of the system.
Right.
So how does this RVTE actually monitor what's going on at these boundaries?
Okay. So they dive into two key aspects. There's control flow monitoring, and there's data flow monitoring.
Okay.
Control flow that focuses on the execution path of the code.
Right.
So using RV techniques, you can define like these expected behaviors.
Okay.
And any deviation from those expectations that could signal a bug or, potentially even an attack.
So control flow is like making sure the execution path of our code isn't being like hijacked or something.
Exactly. Yeah.
Okay. That makes sense. But what about the data itself? Like, how do we ensure that that sensitive information doesn't leak out during these processes, especially, when you're dealing with these complex systems like robots that are interacting with the real world and all that.
Yeah, that's where data flow monitoring comes in. It tracks how sensitive data moves through the system. So they talk about techniques like dynamic taint tracking,
Okay.
which basically you mark sensitive data and you follow its path through the system.
Right.
And then there's taint inference, which that focuses more on monitoring the outputs of the system, looking for any signs of leakage.
I see. I see.
They, both of these techniques have their trade-offs.
Okay.
Taint tracking is, it's very precise, but it's also computationally intensive.
Right.
And taint inference, that's more lightweight, but it might not catch every single leak.
So it's like a trade-off between precision and efficiency.
Exactly, yeah.
Okay. It sounds like RVTE adds a significant layer of complexity to the whole system.
Yeah, it does.
But how does it handle different kinds of threats? I'm sure attackers can try to compromise the system in a lot of different ways.
Right. So they focus on two main threat models. The first one assumes that the attacker has non-privileged access.
Okay.
So basically, they're in the system, but they don't have high-level permissions. Okay. And then the second threat model, which is more serious, assumes that the attacker has gained full system privileges.
Oh, wow.
So basically, they have the keys to the kingdom, so to speak.
Okay, so two levels of intrusion.
Right.
So how does the paper suggest, mitigating these threats?
Well, for the non-privileged attacker, they suggest leveraging containerization technology.
Okay.
So, tools like Docker allow for process isolation.
Right.
They can restrict access to system resources.
So it's like sandboxing the RV monitor and the instrumented applications.
Exactly. Yeah.
So even if the attacker gets in, they're kind of limited in what they can do.
Right. Their reach is limited.
Makes sense.
Right.
But what about when the attacker has full system privileges? That sounds a lot harder to defend against.
Yeah. In that scenario, prevention becomes a lot more difficult. The focus shifts more towards detection.
Okay.
So they propose tamper evident logging. So basically, you create these cryptographically protected log files that immediately reveal any modification attempts.
Oh.
So even with full access, the attacker's actions, they leave a trace.
Okay.
And they specifically mention CLFS, which uses cryptographic techniques to ensure the integrity of those log files.
So it's like having a security camera that can't be tampered with.
Exactly.
Got it. That's fascinating.
Yeah.
But this has all been pretty theoretical so far. Does the paper actually does it get into how these concepts apply to robotics?
Oh, absolutely.
Where the stakes are arguably the highest.
Yeah, for sure. In fact, a significant portion of the paper is dedicated to the implementation of RVTE in robotic systems using ROS, the robot operating system.
Okay.
This is where it gets really interesting, I think, especially for this audience.
Yeah, that's where the real world applications start to come in, So tell me, how does RVT fit into this whole ROS world? Like, does it play nice with existing tools and frameworks and all that?
That's a great question.
Yeah.
And we'll definitely delve into those practical aspects in the next part of our deep dive.
All right, sounds good.
Yeah. So the integration of RVT with ROS is actually pretty seamless. ROS being, a widely used framework for robot development, it's got this rich ecosystem of tools already, and the paper highlights this tool called RS monitoring.
Okay.
It's specifically designed to observe events and communications within ROS applications.
Okay.
So it's like having this built-in monitoring system, that gives you all this data for analysis.
So we can basically feed this data from ROS monitoring into RVT.
Exactly.
And get real-time insights into what's happening inside the robot software.
Precisely. They actually demonstrate a prototype that combines RS monitoring with another RV tool called Larva.
Okay.
And Larva is used to define and enforce specific properties, make sure the system's behaving as intended.
Okay.
So it's like, setting up rules and constraints that the robot's software has to follow.
Right.
ROS monitoring provides the data, and then Larva acts as the enforcer.
Right. Yeah.
Flagging any violations.
I'm starting to see how this this layered approach, with the T's, the RVT, now these tools like Larva and ROS monitoring,
Yeah.
how it can really enhance the security of these robotic systems.
Yeah, you're getting it.
Yeah.
And the beauty of this approach is that it's really modular.
Yeah.
You can swap in different RV tools depending on the specific needs of your application.
Yeah.
The author specifically mentioned deploying Larva in a separate container.
Yep.
They call it the forensic node for added security.
So it's like having a dedicated security analysis unit inside the robot system.
Yeah, that's a good way to think about it.
Okay. That makes sense. Isolating that monitoring process, it adds another layer of protection.
Right.
But ROS itself has had its own security challenges.
Yeah.
Especially with the earlier ROS 1 version.
Yeah.
How does RVTE address those inherent vulnerabilities?
Well, you're right to point that out. ROS 1, it wasn't initially designed with security as a primary focus.
Right.
Communication between nodes, for example, it was largely unprotected.
Right.
So it was susceptible to eavesdropping, manipulation, things like that.
Yeah.
The paper acknowledges these weaknesses, and they emphasize that RVT can provide a much needed layer of protection even in these less secure environments.
So even with ROS 1's known vulnerabilities, RVT can kind of step in and add that extra security.
Yeah. Exactly. Yeah.
Okay, that's reassuring.
Yeah.
But ROS 2, the newer version, it's supposedly addressed a lot of those security shortcomings.
Right.
Does RVT still offer benefits in ROS 2 environment?
Oh, absolutely. While ROS 2 has made significant strides in security, they introduced things like encryption, authentication for secure communication.
Yeah.
But no system is foolproof, right?
Right.
Sophisticated attackers can still find ways to exploit vulnerabilities.
Yeah.
So RVTE provides this proactive defense. It can detect and potentially prevent attacks, even if the underlying system has some weaknesses.
So it's like having a security system for your security system.
Yeah, exactly. Yeah.
Okay. You can never be too careful, especially when you're dealing with systems that have real world consequences.
Right.
So in both ROS and RS2, RVT can enhance the security posture and protect against a wider range of threats.
That's right.
Okay, that's a pretty powerful proposition.
Yeah.
Does the paper talk about any specific implementations or use cases within the ROS ecosystem?
Yeah, they specifically highlight the use of ROS monitoring in conjunction with RVT to protect the communication between a secure node, which would represent the T,
right,
and other nodes within the robot's network.
Yeah.
This is really crucial when you have sensitive data that needs to be exchanged between different parts of the robotic system.
Yeah.
Imagine a scenario where you have a robot that's collecting sensitive data in a hospital environment, for example.
Right.
RVT could ensure that data is transmitted securely and remains protected, even if other parts of the robot system, are compromised.
Okay. Now, no, that's a real world application that hits close to home.
Yeah.
Secure data handling is it's so important in healthcare.
Absolutely.
And this RVTE approach, it seems like it could offer a real advantage there.
Right.
But the paper doesn't just focus on securing individual robots, does it?
No, it doesn't.
It also talks about securing the communication between machines, right?
Yeah, that's a great observation. They recognize that robots often operate as part of larger systems that communicate with servers, cloud platforms, other machines.
Yeah.
And securing those interactions is just as critical as securing the robot itself.
For sure.
So they discuss how RVTE can enhance the security of data distribution service, or DDS, which is a standard for real-time data exchange that's commonly used in ROS 2.
So it's not just about protecting the robot in isolation. It's about securing its interactions with the whole ecosystem that it's operating in.
Exactly, yeah. And they go even further. They emphasize the importance of securing the RV monitor itself.
Okay.
Because if the monitoring system gets compromised, then the whole security framework could crumble.
It's like having a security guard for the security guard.
Right,
You
exactly.
got to make sure the tools that are protecting your system are themselves protected.
Yeah, yeah.
Yeah. So does the paper does it propose any like solutions for securing the RV monitor?
Well, they get into various challenges and future research directions.
Right.
One intriguing proposition is running RV components within the T itself.
Right.
So, you'd create this self-monitoring security enclave.
Oh,
Imagine the T not only protecting sensitive operations, but also continuously verifying its own integrity.
that's taking layered security to a whole new level.
Yeah, it
A
is.
key that can like introspect and maybe even defend itself against internal threats. It's a fascinating concept,
It is.
but I'm sure it comes with its own set of challenges,
Oh
right?
yeah, definitely. Ts, while they're very secure,
Right.
they're also resource constrained environments.
Okay.
So implementing RV within a T, that would require careful optimization
Right.
to avoid impacting performance or compromising the T's security.
Yeah.
It's a delicate balancing act, finding ways to enhance security without introducing new vulnerabilities.
It sounds like we're just scratching the surface of what's possible with this runtime verification in trustworthy computing.
Yeah, yeah, for sure.
This paper lays out a pretty compelling vision for the future,
It does.
and I'm excited to see how these ideas evolve and shape the landscape of robotics and beyond.
Yeah.
But before we get too carried away with the future, let's bring it back to the present for a second. Could you summarize the key takeaways from this paper for our listeners who are deeply involved in the world of data science and machine learning?
Sure. Sure, yeah. This paper really makes a strong argument for using runtime verification, especially this RVTE thing
Right.
in building these trustworthy computing systems.
Yeah.
They show pretty convincingly that just relying on traditional security measures,
Yeah.
it might not be enough anymore, especially with these increasingly complex systems we're seeing, like robots and stuff.
Yeah, that's a key takeaway for sure. It's not about like getting rid of the old security practices, but more about like adding on this extra layer of real-time monitoring and verification.
Right.
It's almost like having this constant audit trail for sensitive operations. Making sure that they're following the rules and constraints.
Yeah. Exactly, and they illustrate this really well with the integration of RVTE into the ROS ecosystem,
Right.
which our listeners are pretty familiar with, I'm sure.
Yeah, for sure.
Leveraging existing tools like ROS monitoring and integrating these specialized RV tools like Larva
Yeah.
provides a pretty practical way to actually implement these concepts.
And the modularity of this whole approach is really appealing too.
Yeah.
It lets developers kind of tailor the security measures to the specific needs and risks of their applications.
Right.
Whether it's using taint tracking to make sure the data is good, or using tamper evident logging for like forensic analysis.
Yeah.
There's a whole toolbox of techniques that they can use.
Exactly. And another key takeaway is that the paper doesn't just present this theoretical framework. It actually gives you concrete solutions and implementation details.
Right.
They acknowledge that real world deployments are complicated.
Yeah.
Things like the need to secure the RV monitor itself.
Right.
And they offer some potential strategies to address those challenges.
That idea of running RV components inside the T itself is pretty interesting.
Yeah.
It's like creating these truly self-monitoring security enclaves where trust is kind of built into the very core of the system.
Yeah.
It's a really thought-provoking idea, and it shows how security is constantly evolving in this whole world of trustworthy computing.
Definitely.
So for our listeners, who are already deep into data science and machine learning and all that,
Right.
this paper is kind of like a call to action. You know? It shows how important it is to start thinking about security at every step of the development process, especially as our algorithms and models and stuff are are starting to make their way into the real world through robots and autonomous systems.
Absolutely. So we can't just focus on our, accuracy and efficiency anymore.
Right.
We also need to prioritize trustworthiness. Making sure that these systems operate securely, reliably, predictably.
Yeah, for sure.
And this paper, it gives us a roadmap to get there.
So as we wrap up this deep dive, I think the main takeaway is that runtime verification,
Yeah.
especially RVTE.
Right.
It offers this powerful and practical way to make sensitive systems more secure.
For sure.
And by integrating these concepts into our work, we can start building a future where trustworthy computing is just the norm.
Yeah.
Where we can responsibly and safely deploy robots and autonomous systems across all sorts of different areas.
Well said. Well said. It's a future worth working towards.
Absolutely. Well, thank you for joining us on this deep dive.
Yeah. Thanks for having me.
And until next time, stay curious and keep exploring this ever-changing world of trustworthy computing.